Okay, we mentioned that given a vector field x say equal to xi dx plus eta dy, then all the functions f of xy that are invariant under x satisfy x on f equal to 0. In fact, we use that equation, which is a first order linear PDE we showed, to find all the functions f of xy invariant under this one parameter Lie group of transformations. If we want all the functions that are of xy and y dashed, then those that are invariant under x satisfy the vector field x prolonged on G equal to 0. And similarly, if we want all the second order functions, second order derivatives that are invariant under x, then we solve such functions from the PDE x2 on G, x2 on H rather, equal to 0. So in this last case, x2 on H equal to 0, we will be able to determine all the zero order functions of that type, all the first order functions of this type, and in addition all the second order functions that are invariant under this vector field. But there's an important theorem that says that if we know the zeroth order or a zeroth order invariant function under x, suppose that function is u, so suppose u is a zeroth order invariant function, and suppose v is a first order, in derivatives of course, first order invariant function under x, i.e. x on u is equal to 0 and x1 on v is equal to 0. U is a zeroth order, v is the first order. Then the theorem says that a second order invariant can be obtained, well, from what we had above. We just need to solve x2 on H equal to 0, but if we know the 0 and first order, then a second order invariant of x or under x is the derivative of the first order invariant with respect to the zero order invariant. And this theorem is important in the reduction of ordinary differential equations. So in that last example, and I'll take the easier one, we showed in the previous lecture that the ordinary differential equation y double dashed plus y minus y to the minus 3 equals 0 is invariant under a number of vector fields. In fact, it's a Lie group with bases under what I call x1, x2, and x3. x3, recall, was the translation in x. So I'm going to use x3 merely to demonstrate how we use this theorem to reduce the order of this differential equation. Right, so the previous theorem says we need to find the zero order and first order invariant. If we take x3 and prolong it once, we get d by dx plus 0 d by dy. That's obvious. And of course, if you use the formula for eta 1, then we get that eta 1 is also 0. Right. So the functions that are invariant under x1 will be given by solving the following. So the functions f that are functions of, say, x, y, and y dash, perhaps I should call it g, in line with the previous notation. So the functions of x, y, y dashed that are invariant under x is equal to 0, and that implies that dg dx plus 0 dg dy plus 0 dg dy dashed is equal to 0. Or we said to solve for g, we write the characteristic form dx over 1 equals dy over 0 equals dy dashed over 0. So these equations, because we have three variables x, y, y dashed, we require two integration constants or two independent invariants. The dependent invariant, of course, is then determined by solving dg over 0 with that. Now, it's very convenient here that since dy is over 0 and dy dashed is over 0, the two independent invariants are rather straightforward. Right, so we have two independent invariants, perhaps I should call it u. So u is equal to y, that's an independent invariant, and u is equal to y dash, v is equal to v is equal to y dashed. This would serve as our zero order invariant. This one is first order invariant. Then by the theorem, a second order invariant of this vector field x3 is the derivative of v with respect to u. Now continuing from here on, using the chain rule, this is dv totally with respect to x, du totally with respect to x. Right. If you differentiate v totally with respect to x, you get y double dashed. If you differentiate u with respect to x, you get y dashed. So now we can replace y double dashed. Y double dashed is y to the minus 3 minus y, substituting the equation, over y dashed. And now, if you replace everything in terms of the invariance, you get, this is u to the minus 3 minus u over v. So this then is a first order ordinary differential equation in u and v, which obviously can be solved very easily by variables, separable, etc. So we've reduced our second order ordinary differential equation using one of the vector fields that leave it invariant, namely x3. We've reduced it to, in terms of the invariance of x3, we've reduced it to this first order ordinary differential equation. We could have used x1 or x2, and we would have reduced it to a first order invariant, in first order ordinary differential equation. So this is a standard procedure to determine or to construct, to reduce an ordinary differential equation using a one-parameter Lie group of transformation, or equivalently the vector field to reduce the order of the differential equation.